Good morning, good afternoon, good evening, whatever the case may be. We are back and better than ever. And today we are continuing our exploration of complex numbers, talking about modulus. So let's get to it, shall we? That was the bleachers. I miss those days. All right, so absolute value. What is absolute value? Absolute value is the distance from 0, and generally we think of that as on the space on the number line, right? So what about modulus? Well, modulus is another word for absolute value, but generally used with complex numbers as the distance from the origin. So with absolute value, we're talking 1 dimensions, modulus 2 dimensions generally, but both really are the distance from 0, okay? So the modulus of the complex number z equals a plus bi is the length of the vector ab, which is the real number mod z equals the square root of a squared plus b squared. About this vector format, in case you have not had vectors, this is a vector format. It's component form. A is the horizontal component, and B is the vertical component. So we've talked a little bit about vectors already, but let's just say I had the component form of a vector as 5, 7, and this is in the real number system. All that means is I could start anywhere, let's say here, and I go over 5 units, and I go up 7 units, and this is the vector 5, 7, yes? And with vectors, we talk about the magnitude of the vector. That is the length of the vector because it represents a force or a speed or something like that. Well, we got a right angle here, yes? So to figure that out, I use the Pythagorean theorem, which is the square root of 49 plus 25, 49, 59, 60, 74. Square root of 74 is the magnitude of this vector. Well, with complex numbers, we refer to it as the modulus because that would be the distance from 0. So this is the complex number 3 plus 2i, and its distance would from here to here, the distance from the origin at the end of this this complex number would be the square root of 3 squared plus 2 squared, which is the square root of 13 by Pythagorean theorem. So find mod z for any of these. Well, it's going to be the same what we just did, square root of 3 squared plus 2 squared, a squared plus b squared, right, is 9 and 4 is 13. And if we just graph those real quick, 3 plus 2i, 3 minus 2i, and negative 3 minus 2i. Clearly, you can see all those distances are the same from the origin. Sorry about the sloppiness of the Argon diagram. We have some properties of modulus here. A lot of them make sense. I'm just going to show you this one real quick. So let's just let z equal a plus bi, right? So the modulus of z star is equal to the modulus of z. Well, so the modulus of z star would be the modulus of a minus bi, right? And we need to show that's equal to the modulus of a plus bi, right? So this would be equal to the square root of a squared plus negative b squared, and this is equal to the square root of a squared plus b squared, and clearly this is equal to a squared plus b squared, which is equivalent to that. So there we have a general proof. So let's move on to an example here. Prove that modulus z1, z2 equals z1 mod z1 times mod z2 for all complex numbers z1 and z2. So we're going to let z1 equal a plus bi and z2 equal c plus di. Okay, and we're going to first take a plus bi for the left side, a plus bi times c plus di, and I will tell you that that is equal to AC minus BD squared, just trust me on the algebra, plus AD, or you can probably see it, plus BC squared. Okay, and so the modulus of that is simply the square root. Sorry about that, Mr. 2. We'll fix that. And that is equal to the square root of AC squared, or A squared C squared minus 2ABCD plus B squared D squared plus A squared D squared plus 2ABCD plus B squared C squared. A lot of fun algebra there. And let's extend that square root. That's pretty terrible. And clearly, kapow, kapow. And finally, we can get this down to the square root of c squared plus d squared times a squared plus b squared by gathering some like terms and doing some factoring, which is equal to the square root of, parenthesis, a squared plus b squared times the square root of z squared plus d squared, which is mod of z1 times mod of z2. So algebraic proofs are, you got to crunch some algebra out, but it's not all that terrible. Here's an example. So find the modulus of z given this equation here. Okay, so we have this. If we square both sides, I get 5, or 25, I should say, modulus z minus 1 squared equal to modulus z minus 25 squared. Okay. Well, why do I do that? Well, I should be able to see, or the reason that I'm doing it is that's equal to 25 times z minus 1 times z minus 1, minus 1 star. And then the right side is equal to z minus 25 times z minus 25 star. And that is because of the property that was on the modulus property page, which you would have access to, that the mod z squared is equal to z times z star. So that's all. I recognize that, and that's why I squared both sides. And from that, get 25 times z minus 1 times z star minus 1 is equal to z minus 25 times z star minus 25. And where do I get that? And again, this will be available to you. I get it from that property of moduli. That, I believe, is from the second one's from chapter 6, I believe. So now, as we expand, we get 25z star minus 25z minus 25z star plus 25 is equal to zz star I want to make a ZZ top joke, but I won't, but I guess I sort of did. Minus 25Z minus 25Z star plus 625, 25 squared, of course. Okay. And if we clean all of that up, we end up with 24ZZ star is equal to 600. So ZZ star is equal to 25. And ZZ star is equal to mag Z, or mod Z squared from this property right here. So that is equal to 25, which means if I take the square root of both sides, that mod Z is equal to 5. Nice little algebraic problem, and using some properties. And we know it's equal to 5 because we know that mod Z must be greater than 0. Moving along, distance in the number plane. Same ideas here. If we have P1, P2 are 2 points in the complex plane, which correspond to the complex numbers Z1 and Z2. We know that this is the magnitude, which simplifies to this, which simplifies to this, and it is the distance between P1 and P2. Or we could look at it this way. I'm not going to bore you because you can pause and read through it, which leads to this. If Z1 is equal to OP sub 1, O being the origin, Z2 equals OP sub 2, then the modulus of Z1 minus Z2 is the distance between the 2 points. That is a nice, handy little formula to have. And we have a connection in coordinate geometry. You can pause and take a look. I don't want to take time on the video, but it's a very nice connection to Euclidean geometry. But let's go ahead and do this example. 2, 3, and 6, 1 are 2 points on the Cartesian plane. Use complex numbers to find the distance between PQ. So instead of 2, 3, we're going to think of Z as equal to 2 plus 3I. And we're going to think of Q as, or not Q, W as 6 plus I. And so for the sake of time, I skipped ahead just to show you the work because the work is very simple. But it just comes down to the connection between coordinate geometry and distance in the number plane using complex numbers using this formula. Or this formula, I'm sorry, modulus Z1 minus Z2 is equal to modulus P2 P1. The distance between P1 and P2. So I use those formulas here. The midpoint formula, you're just going to add them and divide by 2, and that is how we ended up with the point, well, 4 plus 2I, with how we defined our Z and our W corresponds to the Cartesian point 4, 2. More example. What transformation moves Z to IZ? Seems like a weird question. But let's let Z equal X plus IY. And you could do A plus BI, doesn't matter. Then IZ is equal to XI plus I squared Y, which is equal to negative Y plus XI. So our complex number has changed. The real and the imaginary parts have changed. So if we think of Z being equivalent to, that's a symbol for equivalent to, the point XY, that's a nice symbol when it's actually not equal, then IZ, I times Z, is going to be equivalent to the new point P, the translated point P, negative y x. So mod Z is equal to square root of x squared plus y squared, and mod IZ is also equal to the square root of x squared plus y squared. So therefore, from OP prime, from the origin to P prime, is the same distance as from O to P. So Z, from this, we can tell that Z moves to IZ under an anti-clockwise rotation of pi, so I'm going to say anti-clockwise rotation. So that's going to be this way, of pi over 2 about the origin. And let me do just a quick sketch up here. Okay, so if we have the point xy, let's just say we have this x, y, right here, that's P, then negative y, so about here, negative y, the same distance, and x, you can kind of see how that would form a right angle. It's just, switching the x and the y's and negating, and how the rotation would be pi over 2 anti-clockwise. I guess instead of anti-clockwise, we could have said negative pi over 2 about the origin. All right, so that is all I have. I hope you enjoyed it. I know that I did, and with that, I am